a recording and I try to share one screen. Okay, I'm sharing the screen right now, and okay, so maybe let's do a bit of a recap, or kind of what worked from what I told you last week, and what kind of complications appeared when I tried to implement it. So the point of the algorithm, if we are doing a bit of a recap, is that we are doing pattern unification, but when we are doing a spine inversion, the spine inversion can recursively perform more pattern unification, which can perform more pattern unification and more spine inversion. So we have this generalized spine inversion, which can go arbitrarily deeply into the spine, and then it performs recursively more pattern unification in order to get the inverse substitution. So what was a slightly more interesting example? Yeah, so we had this example where in the gamma context we have a function which returns a pair. So we have a bound variable in context which returns a pair, and then we have a meta variable alpha which is applied to this lambda x dot and then the first projection of f of x. So essentially this meta variable is applied to just one component of f, which goes from A to B. So if I'm writing this function, f of x dot 1, then this goes from A to B. So we can imagine that this function can be split into two functions, and one returns the first projection and the other one returns the second projection. And here we have a meta which is only applied to this first splitting of this function, and then we have something on the right hand side. In particular, here we have exactly the same function appearing on the right hand side, which is in the spine, and then we also have like a true, so this is a pair of something and a bool. And now we want to solve this equation, but then with the usual pattern unification, the problem is that usual pattern unification can only handle an equation like this if we only have just plain bound variables in the spine. And this is not just a plain bound variable, but it's instead the splitting of a bound variable. And what I mentioned is that basically what we want is that the pattern unification algorithm knows about, so pattern unification should know about the so-called definitional isomorphisms. And the definitional isomorphisms are, so we have currying, which means that we can convert a pi which goes from a sigma into an iterated pi, and this is an isomorphism up to definitional equality. And we also have flipping. We can always permute the arguments of a function, and then we can also do the axiom of choice, or columnization, which is kind of swapping a sigma with a pi. So the generalized pattern unification algorithm works in a way such that we can transport a bound variable using currying, flipping, and axiom of choice in an arbitrary complicated way, and the pattern unification algorithm still knows what should be the inversion of this thing. So in this case, the bound variable is f, but actually we are using this columnization of this function, which is a arrow b product a arrow c, and then we are using a currying of the local context, because here gamma has just a single variable f, but we can do a currying in the context so that we get a new context which has f, which is split into these two functions. So first we can use a columnization on this function, and then we can use a currying in the local context. And so we have like a gamma 0 and then a gamma 1. So we can create a new gamma from the old gamma, which is curried. And then we can solve the solution in this curried context. Okay.
So, sorry, what's the relationship between the original gamma and gamma 0, f0, f1, and gamma 1? Because originally you didn't have f in gamma at all, right?
No, I did have, because here I have that f is a variable in gamma, so the original gamma looked like this.
Ah, okay, I get you.
So the original gamma looked like this, and here we say that we are performing a currying on gamma, but first we have to columnize and then we can curry the gamma. And the generalized algorithm should know about all these things, and we can apply this in the spine and also in the local context, and in principle we can also apply this transformation to the meta itself. And
so this would be directed, right? So you're trying to get a normal form, because otherwise how would you know which way to keep transforming?
Okay, Gergo, I guess you haven't seen the recording of the last week or the week before.
Oh, okay.
Because I can do a quick recap, but the whole point of this is that there is a kind of the old way, the old algorithm, and the old algorithm works by applying currying plus axiom of choice to everything, and then the result of doing this transformation is that everything related to sigmas disappear from the unification problem. So sigma disappears from unification problem, and then we can simply use the primitive naive pattern unification algorithm. So if we apply this transformation to gamma and also to the meta variable itself, then we are not going to have any sigma anymore, because every pair is curried away. So if we have like an alpha tu, then it gets curried away and it becomes alpha tu. And if we have an alpha applied to like x dot 1, then it gets curried away in the local scope. So if this is a bound variable, then we curry the local gamma, and then this becomes like an x1, and x1 is kind of a freshly inserted bound variable, which is the first projection of x. And if we have an alpha, maybe xy, and then we take the first projection of this thing, then we use a currying in the meta context, because we see that here we have a meta which returns in a sigma, but then we can split it into multiple metas which return all the projections. So then we can curry the meta context, and we get that we have an alpha 1 xy. Okay, so the result of doing systematically this currying and columnization everywhere, we can eliminate the sigma related, like all the projections and all of the pairing constructors can be eliminated from a unification problem. But then an issue with this old algorithm is that it's not very efficient, because whenever we are performing like this kind of currying of metas, this kind of eta expansion and currying of meta variables, we actually have to compute all the new types of the meta variables. So, and we also have to create a fresh meta variable for every projection of this expanded meta. So the problem with the old algorithm is that it creates a bunch of fresh metas and it creates a bunch of new types, and the new types have to be computed from the old types. And then we also have to compute so this currying and this AC are isomorphisms, but we always also have to compute what is the transport of doing this currying and axiom of choice. Like, for example, if we have this gamma and then we transform the gamma, then we have to transform the unification problem with the transporting along this isomorphism of context. So the problem with the old algorithm is that it creates new metas with new types, and we also have to perform a bunch of transport along this combination of currying and AC. So this was the first problem, and then the other problem is that we are not able to take into account the flipping isomorphism. And as you mentioned, Gergő, the problem with flipping is that it's not directed. So it is not possible to pick out the right direction to flip things to. So it's not directed, and it depends. So the direction of it's not a problem, and I'm finishing very soon with this recap. So then the problem is that the flipping doesn't work because it's not directed, and we have to figure out the right direction of flipping, but we can only figure out the right direction of flipping by going into the spine and looking at what kind of things we have there. But then the problem is that if we have to look into the spine, then we have to use a different algorithm, because the point of this old algorithm is that we do not want to look into the spine, we just want to transform it into a nice kind of spine, and then we use the simple version of pattern unification. But here we already have to look into a more complicated spine, so the solution should be that we have a more general algorithm which does all of this like all of this extra transformation, does everything on the fly while we are looking inside a possibly more complicated spine. So the solution is that we have a generalized algorithm for doing the inversion on the spine. Okay, and the point so the algorithm works like the following way. So let's just repeat this example. So my convention on the last week was that whenever I have a problem like this, essentially the algorithm works by unifying every entry in the spine with a bound variable, but in the bound variable which we will have in the solution of this alpha meta variable. So if you have a problem like this, then we already know that the solution will look like this. And if we have De Broglie levels everywhere, then we already know that whenever we have any unification problem, then the solution will be a lambda looking like this. And for illustration purposes, the convention which I used last time is that I'm naming, in a unification problem, I'm naming all the bound variables starting from x, but also using f and g and h for functions. And whenever I want to refer to the variables, to the bound variables of this eventual solution of the meta variable, then I'm starting the naming of the bound variables from a, b, c, and so on. So if you think about it, the solution will be like this. And now I have to do an inversion of this spine. So I want to do a substitution. So the result of inverting the spine of alpha will be a substitution which maps every x, every y, every f, not necessarily every f, but some of these variables in gamma are going to be mapped into expressions such that these expressions can only depend on a, b, c, d, and so on. So we are kind of mapping from the gamma which contains x, y, f, g to the context which contains a, b, c, d, and so on. So this is inverted spine. Gives us something like this, but this is a partial substitution, so we do not necessarily map everything in gamma. We only map some variables in gamma, and it means that like the unification is only successful if the right hand side of the unification problem only depends on the variables which are actually mapped in this partial substitution to something. So we have to do this inversion, and a good way to illustrate the new algorithm is to say that if we have any number of arguments in this spine, so here we only have one argument, but we could have more, then what we are doing is kind of a unification, and we want to unify every argument with the corresponding bound variable in the eventual solution. So let's do a simpler example first. So if I have x, y, z, and I want to unify this with, for example, x, y, which is a function type, then the algorithm works by I just start counting the variables from A. So I'm writing these variables above the entries in the spine, and then I have to unify. I want to map x to A, and then I want to map y to B, and I want to map z to C. And if I'm merging all of these mappings, then I get the inverted substitution, like the inverse partial substitution of this spine. But we can look at a slightly more complicated example, which for example has some eta expansion in the spine. So I can also have something like this. And in this problem, I want to map this lambda expression to A. So I want to perform this, but of course this doesn't work, because on the left side I have something which is not a variable. But I can actually do kind of a decomposition or a generalization of this mapping. So I want to decompose this mapping so that I get a real substitution. So here I say that the lambda x.fx should be mapped to A. Okay, but now I have a lambda on the left hand side and something on the right hand side, so I can do it like this. I can say that for all x, I want to map fx to A of x. So I'm just applying both sides of this mapping to x. So I say that for all x I want to perform this mapping. But now this looks like a pattern unification problem again, right? Because I want to map fx to ax. So now I'm doing recursively a pattern unification kind of thing. And now I have now a different thing, but now I have to get some different fresh variables. I'm not sure what I should call it. Maybe let's call it 0. And now I want to map x to 0, and that's it. So now I'm just having this inversion of this very simple spine, which only consists of this x variable, and I get this. And then if I apply this x to 0 substitution to the right hand side, then of course I will get a0, and then I can do a solution of f using the usual pattern unification, which is that f should be mapped to lambda 0 dot a0. So you can see that I started out wanting to map a lambda expression to something, but then I did this kind of decomposition and I recursively used the pattern unification, and then I got a normal mapping of this f variable to a lambda expression. Okay, then I have to map y to b, but that immediately succeeds. So as a result, I get f mapped to lambda 0 dot a0 and y mapped to b. And now I can apply this substitution on the right hand side of this problem. So I get the solution, which says that lambda ab dot so f becomes a, and okay, this is actually not solvable because I haven't mentioned x in the spine, but if I replace it with y here, then it becomes ab arrow b. Okay, so this is the algorithm, and the nice thing about this algorithm is that we can only so we only have to eliminate the projections from any problem. So we don't have to, so flipping and currying and sum AC is completely automatic, and the only kind of extra processing step which we have to perform is eliminating projection. So we only have to eliminate projections as extra step. Okay, so for example, if we have a problem like alpha, the first projection of alpha, we want to unify it with something, maybe u, then here we cannot do any magic, we cannot do any cheating, because this problem is only about the first projection of a meta variable. We really have to expand, we really have to eta expand alpha, so that alpha is first solved to be like this pair of two meta variables, and then we get a new problem. Well, let's maybe call it alpha 1, alpha 2, and then we get a new problem, and then we just solve it as usual. So here we solve the first projection, but we have no idea about the second projection, so we really need to create a fresh meta variable for the second projection. So this is a step which cannot be avoided by doing any kind of generalized inversion magic. So we have to do this explicitly. And but we do not have to do any other transformation on metas or meta contexts, and we do not have to compute any new types besides doing this expansion. However, we have to do this projection elimination by doing some kind of eta expansion, but we also have to do it on local variables. So if we have this kind of problem, So we have a gamma, and in gamma x has type A product B. Then we still have to do this projection elimination on the bound variables in the scope. So conceptually, we still have to do this transformation of gamma. So we still have to transform gamma in a way such that we have x1a, and then we have x2b, and then we have gamma 1. And in this context, x1 is going to be now something which type A, so then the problem can be transformed into a x1, x1. So conceptually, we still have to do this, and we have to do this recursively. So when we are going deep into some spine and we are doing this recursive spine inversion algorithm, like this recursive inversion unification mutual algorithm, then sometimes we have to do this deeply inside the spine. And this turned out in the actual implementation to be one complication, which is not super hard, but which is a bit complicated. Okay, and why was it a bit complicated? So issue with doing kind of like this gamma querying of local vars. Okay, so what's the issue? And so if you want to do it in a naive, straightforward way, it's not super complicated. But the problem is that I want to do it efficiently. And if you think about it, this kind of like insertion into gamma is not efficient, and in the De Bruijn discipline. Right? Because if I'm doing a modification in the middle of gamma, I'm inserting some new stuff into a context, then everything which depends on the context has to be shifted. And so everything which depends on gamma has to be shifted, and this does not change when I move from De Bruijn levels to De Bruijn indices. So with De Bruijn levels and De Bruijn indices, I have the same problem, because I'm doing an insertion in the middle of gamma, then I have to shift all the levels which are after the insertion. But if I'm using De Bruijn indices, then I still have to do a similar kind of shifting. So unfortunately, insertion into scopes is not efficient with De Bruijn discipline. So the only solution which I was able to find is that I need to support a fresh variable discipline as well. So the modification which I had to do in this implementation is that now I don't only have De Bruijn levels in values, so val not only levels, but also fresh vars. But I'm keeping these fresh vars kind of local. So basically, these fresh vars never escape any spine inversion problems. So fresh vars are local to a particular spine inversion problem. So when I'm doing so, and now I can show you a bit of a source code. So what I did is to generalize partial substitution. And let's look at the implementation. So what I did was to generalize a partial substitution, and now it has a bit more stuff. So So in the comment I'm writing that this is a partial substitution from gamma to delta, but it is factored into a total substitution from delta prime to delta and a partial substitution from gamma to delta prime. So a partial substitution now kind of by default includes a total substitution which does these eta expansions in the context. So the total substitution is eta expansion of 0 or more variables, but all of the eta expansion is done by using the fresh variables. And now it's a bit hacky, but the fresh variables are actually represented with negative variables in values. It would be very simple to just kind of separate the fresh variables from the Deborn levels in a nicer way, but this was kind of just a hacky solution which I did. But it would not be hard to do it in a nicer way. So I'm saying that every partial substitution is factored into an expansion and an actual partial substitution, and the expansion uses fresh variables. And this allows us to use fresh variable conversion to insert new expansions efficiently. But because the factoring which we have is like so this factoring of a partial substitution is like we are going from, so if we gamma to delta, right, and then a gamma to delta prime. Okay, so it looks like this. So this is kind of a normal, like a partial substitution, and this one is just an eta expansion. And if you are looking externally at this partial substitution, the fresh variables are not even visible, because the fresh variables are only used internally in this like in this hidden intermediate context in this composition of two substitutions. So I thought a bit about like what is a nice solution for this eta expansion of context thing, and I think that this is a nice solution. So I do not want the fresh variables to infect my implementation. I really don't like using a fresh variable convention in general, but here I had to concede a bit of a ground because this is just not efficient unless we are using the fresh variables. But I still want to hide the fresh variables inside a partial substitution. I do not want the fresh variables to escape from any partial substitution. Okay, so what are the fields? So this is the domain. I'm also using some microlens to do some field overloading. So partial substitution has a domain, which is this gamma, has a codomain, which is this delta, and then it has just a partial substitution, which goes from gamma to delta prime, and this is essentially just delta prime, but this is counting fresh variables. So here I'm switching in delta prime to the fresh variable convention, and I also have a partial substitution. No, this is not a partial substitution, this is total substitution, which is just an eta expansion which goes from delta prime to delta. Okay, and so I think this was the hardest thing to figure out in the implementation, but I have to mention that this kind of recursive nested pattern unification is also not really trivial. Okay, let's try to explain it. Okay, so because now what happens is that if I am trying to do a pattern problem, then this can be either a unification or it can be like this this mapping during inversion. So I have something like this, or I have something like this. So two kind of problems, but in both kind of problems I want to perform exactly the same kind of inversion. So I do not want to duplicate the code of inversion, and actually I cannot really duplicate the code of inversion because I have to do this recursively. So okay, it's a bit wrong. I mean, in principle I could duplicate the code of inversion for this kind of case and also for this kind of case, but I don't really want. So it's much more elegant if I only have one kind of spine inversion, which I can perform in both situations. But then this spine inversion has to be generalized, and it has to be generalized in the following way. So because now whenever I'm doing this kind of problem, then this is not actually an alpha, so it is not a meta variable. It can be an arbitrary bound variable. So if we are looking back to the examples, like here you can see that I want to perform this mapping, and then recursively I'm doing a spine inversion here in this fx-ax problem. But now the variable the variable which is applied to the spine is not a meta variable. It's this f, and it's a bound variable. It's in an arbitrary context. But if we think about the traditional pattern unification problem, here we always have a meta variable in the left side. So the head of the spine, or the head of this neutral expression, is always a meta variable, and the meta variable is always a closed thing. So with respect to the local context. So it does not depend on gamma. But if we are doing this recursive pattern unification or this recursive inversion, then we can have things in an arbitrary local gamma scopes. And this complicates things a bit, because now essentially what I have to do is I have to split gamma into 3 parts. So every gamma is going to look like this. So there is some gamma part, and there is some gamma S part, and there is some gamma P part. So every gamma consists of 3 parts, and the first part, so this gamma, it contains variables which cannot be used in a spine inversion or unification. It's like it contains vars which are kind of irrelevant or cannot be used in a spine inversion problem. And gamma S, so this is S because it's kind of solvable. Gamma S contains vars which we want to map to something in the current spine inversion problem. So because we have this recursive spine inversion, whenever we are doing a spine inversion, we are already doing another spine inversion problem. So this gamma S is kind of the thing which we want to invert right now, like things to invert in a kind of somewhere up in the call stack of doing this recursive inversion. And then there is gamma P, which is the parameter and then this contains bars which are the parameters to a spine inversion problems. So you can see that it's a bit more complicated, and probably I should look at some examples first, just for seeing that if I have some kind of problem, then which part is in gamma, which part is in gamma s, and which part is in gamma p. So let's do just some very simple thing like alpha xy unified with x. So in this case, we have that the gamma part is just empty, and the gamma s part is just the whole context. Okay, maybe just write out. Okay, but maybe I should also write this as gamma u, and then u means that it's unsolvable. Maybe not unsolvable, but I, which is irrelevant. Okay, and let's have this kind of problem. So we are working in gamma, and we just have a normal meta-unification problem. And in this case, what we have is that the irrelevant part of the context is just empty, because here everything is relevant in a way, and the solvable things are just gamma, and the parameters are empty, right? Because here what we want to do is we want to do an inversion which inverts these spines. So this spine is a substitution. Let's also type this. So alpha depends on some delta context and has some type A, and the spine is a substitution which goes from delta to gamma, and the inversion of the spine should be a partial substitution which goes sorry, no, this is the other way around. So it goes from gamma to delta, and then the inversion of the spine should be something which goes from delta to gamma. So because the goal to get this inverted spine, and this inverted spine, it returns in gamma, which means that this substitution is a mapping from gamma bars to delta terms, right? And so because the goal is that I want to create a mapping going from gamma bars, now all the variables in gamma are the things that I want to map to something. So now the entire gamma becomes the solvable, or the kind of the to be inverted part of the context is just the entire gamma. And we don't have any parameters to this spine inversion problem, and we do not have anything which is irrelevant to this spine inversion problem. But what happens if we go a bit deeper? So what happens if we instead have like this simple eta expansion thing? And here, when we start inverting this spine, then we have this kind of splitting of the local scope, right? But when we try to perform this, so let's again name this A and name this B. When we try to decompose this mapping, then we get this kind of thing, right? So we get a gamma x, and we want to do this mapping now. So because inside the spine there can be like lambdas, and we can go under the lambdas. We can get new things in the context which becomes parameters to the spine inversion problem. So if we are going, so here we had like this empty gamma empty. I can just do it like this. So we have an empty gamma empty, but now we have an empty yeah. So when we want to do this problem, then we have this empty gamma empty. But when we start to do this spine inversion, so when we start inversion, then what happens is that okay, nothing happens because this is already the decomposition which is for this spine inversion problem, right. So when we want to perform this spine inversion, then what we have is that we want to map everything in gamma to something, and we don't have anything which is kind of a parameter to this inversion problem. However, when we go under this lambda, then we still want to do this gamma mapping, but now we have an x which is a parameter to this problem, and I have to put this x into the bag of parameters, because this x is not even in the scope of this goal, right? So I cannot just put x into the same context. I have to somehow mark that x is now kind of a parameter to this inversion problem. Yeah, and now I have to do another inversion. So now in this scope I have to do another inversion. But now there is a kind of a mix-up of this splitting of the context, because now what I want to solve is all the parameters. So now I want to map the things which are the parameters, right? Because here this x comes from the lambda binder, and now I have to solve this problem, and I have to invert this spine. But now when I'm doing this inversion, what happens is that the things which are previously parameters become solvable. So the gamma s becomes the old gamma p, and gamma p becomes empty, and the irrelevant part becomes the old gamma s. So kind of new splitting for recursive inversion, right? Because now I want to solve x here, and x is a parameter, so x becomes, in the new problem, what was a parameter becomes a solvable thing. And it's important that I maintain this distinction of solvable and irrelevant and parameter things, because whenever there is a pattern problem, then the head of the neutral expression can only be a solvable thing. So here this is fine because x is a solvable thing, and here when I have this original problem with alpha, this is fine because a meta variable is in this case is also a solvable thing. And maybe it would be also possible to generalize the splitting of the context to the implementation where we can have an arbitrary mixing of bound variables and meta variables. So I think there is a generalization of this algorithm which does not actually distinguish this kind of unification problem for this other kind of mapping problem, Because we just say that like the goal of doing this unification is to produce a substitution which maps the meta variables to something, right? So if we generalize this, then the metas also behave just like normal bound variables. And then we do not have this kind of thing, but we only have this kind of thing. But in my actual implementation, there is actually a distinction between trying to solve a meta variable and trying to map a bound variable to something. Okay, and and here we have this x, and this x is fine because x is now a solvable thing. But we could also have something like this. So we could have a y here. See, so this y, it comes from gamma, but instead of having this eta expansion here, I could also just write lambda x dot fy. But now this fy, if we go recursively into this thing, this fy is actually, it's not invertible, because when we are here, then y is not a solvable thing, because y does not come from this lambda, so it is not a parameter to this spine, but it is instead an irrelevant thing to this spine. So now we get an error. Okay, I'm not sure how clear it is. So it's not a simple algorithm, but so I think you have to spend a bit of a time trying to go through examples to see why it works and how it works. So it is not a simple algorithm, but it's definitely a quite powerful algorithm. Let's look at some examples. And I already spent a bit of a time trying to explain this thing. So let's look at some examples. Yeah. Okay, so here we have this source code here, and now we do not have any kind of interesting problems. I'm just defining the church encoding of propositional equality, which is the very convenient way to get any kind of unification problem which I want. And now I'm also defining this flipping, currying, and uncurrying, because it's also convenient to illustrate like what the unification algorithm can do. Okay, let's just write a new example. So what happens if I have a meta? So here I am just declaring a new meta by introducing a let definition and then defining this m with a hole. So what if I have a meta which goes from this uu function to u, and I just define it with a hole? And then I want to have an expression which is a lambda from an AU, and then I want to have a referral with a given type. So this is just the Idris kind of convention of having an explicit type annotation for something. So if I have this and then I say, okay, this should be UU. I want to do an EQ of MF and then FU and refer. Right, so this is just a simple example for a usual kind of unification problem, which can be solved even in algebra. So if I'm doing x3, then I get the elaboration output. And then we have this, so this 0 is m, So this 0th meta variable corresponds to m, and the 0 is solved with simply lambda x0 dot x0 applied to u. So this is just normal pattern unification. Okay, but what happens if I'm eta expanding this? Then it still works. And I still get exactly the same solution, and I do not get any extra meta variables. Although even in Agda we do not get any extra meta variables for this eta expansion. So Agda can also handle this case, but Agda handles this case by doing an eta reduction. And it's also a bit problematic because eta reduction is not very efficient if we also have sigma types. So if you want to eta contract some pair expression, that requires performing definitional equality checking. But my algorithm does not have to perform this eta reduction because it can just go into an eta expanded spine and just perform this inversion on the fly. Okay, so here we have this. And what if I add an extra argument to f, sorry, and then I say that I'm flipping the arguments of f. But now I also, on the right hand side of the unification problem, I also have to apply f to two things. And in order to make it visible that there is some flipping involved, let's apply f to u, but the second argument is now u arrow u, so the two arguments are not the same. Okay, and what happens now? And now if we go to the solution of 0, you can see that it's essentially it's lambda f dot f applied to u arrow u and u. But if you look at the right hand side of the original problem, it's the other way around. So here what happened is that the inversion actually computed that f should be mapped to the flipping of f, and then that substitution was applied to this right hand side. So the result is that in the solution here we have the right hand side, but the function is flipped. And this is something which does not work in Agda at all. And we can also try to make it a bit more complicated by saying that in the type of m, this function should actually so this function in the type of m should go from a pair, but this f, so this f actually it goes from u arrow u. So f is curried, but in the type of the meta variable, this is in uncurried form, right? And now we can combine a currying with an argument flipping, right? So here this x is now actually a product, and I have to apply f to the first projection of the product and the second projection, but I can also just flip it up like this. Okay, and now we can see that the currying and the flipping is completely automatic when we are computing the right hand side. Yeah, and then we can essentially perform just an arbitrary combination of flipping, currying, and skolemization, and if what we have here can be inverted modulo all the flipping, currying, and skolemization, then we always get a solution to this unification problem. So what other examples did I wrote? Oh yeah, maybe does this work? Yeah, it also works. So here what we have is that I have a meta which is applied to a pair. So this is not a pattern problem because I have a pair here. And this in Agda would require that we create a fresh meta variable, which is the curried form of m. But in my algorithm, we do not have to create any new fresh meta variable, because like a spine which has a pair inside can be inverted in the recursive way. So here, the solution, yeah, it's just does the first projection. So here you can say that m applied to a first projection and a second projection should be equal to a first projection. So then the solution of the problem is that a applied to something is equal to the first projection of the something. Okay, what else do we have here? Yeah, this also works. Yeah, this is just the same thing, but here. Yeah, so here in the spine I have a flip of a curry of an F and a curry of a G, and it still works. Okay. Yeah, and then this is, maybe this is a bit more interesting, because here what we have okay, maybe not this one, but this one is a bit more interesting. Okay, and why is this interesting? So this is a bit more interesting because here I have, so this is the left hand side of the unification problem. So lambda xy dot and then fyx dot 1. So here this kind of thing requires the scolamization. So this would require the scolamization, but now it's a combination of a flipping and the scolamization. So here this requires to eta expand this function into two functions, and the first function returns the first projection in the end, and the second function returns the second projection in the end. And on the right hand side you can see that I'm calling this function with two arguments, but in the end I'm using the first projection of this result. And this is something which really it doesn't work in Agda in any kind of way, because here we have to figure out that in this function application, even though this function can be applied to any kind of things, because we are taking the first projection of the result, this is still a well-scoped solution, because it really only depends on the first component of this f. And here in this referral, I have to explicitly write out the value argument, because I haven't yet implemented pruning in a nice way, and this requires, so if I only write an underscore here, then this requires pruning, and it requires the kind of pruning which I haven't yet implemented. But if I write this here, then you can see that I get this kind of solution, so that meta is solved to be lambda x0, and then x0 is applied to this. Okay, so it took a while to explain and demo this. So it turned out to be a bit more complicated than I expected, and it also requires some fresh variable convention handling. But I still think that it's pretty good. And this flipping and currying and whatever, so I don't know what's your opinion on it, but I think that it's pretty impressive, because this is just completely beyond Agda. So if you try any of these examples in Agda, they don't work. You get some yellow errors. So yeah, maybe I can also talk a bit about pruning. Okay, so this algorithm that I was talking about last week, it seems to work. Like everything which I mentioned seems to work fine, but for pruning, I was not able to figure out an upgrade which is as nice as this upgrade for the pattern unification. So I kind of have, I like this, so I have this upgrade for pattern unif. It's fine, but is there some upgrade for pruning which is as nice? Because we, like, how can we do a pruning when we have something like an alpha of xy xs xx, and I want to prune maybe y from alpha. So I want to prune the second projection of the first argument of alpha. So how can I do this? And then we still have the old kind of solution. So we still have the old solution. Yeah, so the old pruning still works fine, but the problem is that now there is a mismatch, because the pattern unification, yeah, so old pruning, old intersection works exactly the same way, but now there is an imbalance, because the pattern unification is much stronger than the pruning, and it would be nice if we had a pruning algorithm which has a similar strength to the pattern unification, because the pattern unification produces some inverted spines, and then using the inverted spines we have to perform some prunings, and it's a bit inconvenient if the unification problem fails, because we cannot do the pruning, although we have a very general algorithm for doing the inversion. So that's why I tried to do an upgrade for pruning as well. But let's look at the old solution. So the old solution is just to query and eta expand alpha, and then all the pairs and projections disappear, and then we can do pruning as usual. And pruning as usual, so in the simplest form, pruning as usual is just that we have a spine consisting only of rigid variable headed expressions, and then we are just pruning the arguments from the meta variable which have these illegal variable occurrences. So like if I have alpha xy and I want to prune x from alpha, then the result of this pruning is that alpha is solved to be lambda ab dot alpha prime b. So we are creating a fresh meta variable which does not depend anymore on the first argument. So this is the usual pruning, and the usual pruning works in a fairly straightforward way. If we say that in this spine we can have actually not just variables but also neutral expressions, but the neutral expressions have to be headed by a bound variable. So this can be like x sp1 and y sp2, and then this still works and we are not losing any solutions, but this is kind of we cannot really go beyond this using the old algorithm. But it would be better to do a pruning where we are able to prune not just arguments from a meta, but we are also able to prune projections of arguments of a meta. So like definitions of args of a meta, like if I have an alpha xy and then I want to prune x, then what I want to have is that alpha is solved to be lambda a dot alpha prime a dot 2, and then alpha prime does not depend on first projection, the first argument. Right, so this is what I want to do. But if I want to make it as general, or if I want to do an analogous generalization, then with the pattern unification generalization, then maybe I also want to do something like this kind of pruning. So I have an alpha, and then the alpha have a lambda x dot fx dot 1. Okay, and then what if I want to, okay, yeah, this is not a good example, but this can be a good example, I think. Right, and now what if I only want to prune f from the spine? And I mean, if I want to do it by hand, then it seems to be possible, because in this case alpha has this type, so it goes from some A arrow B C to D, if this is the non-dependent case, and I just want to create a pruned fresh meta variable which only goes from AC to D, and then I solve the old alpha with lambda f dot alpha prime lambda x dot fx dot 2. So alpha gets an f function which returns a pair, but alpha prime only gets a function which returns a c. So here I want to define alpha with an application of this alpha prime. So this seems to be sensible, and this seems to be exactly the kind of generalization which we would like to have. Okay, but what's the problem? And I think the biggest problem here is that this requires not only partial substitutions, but also partial values or terms. And the partial values and terms are like a really unorthodox extension of the core theory, and it makes things a bit complicated, and I haven't yet really figured out like what's a nice way and what's an efficient way of even just handling these kind of partial values or terms in evaluation or in general. Okay, so but why is this the case? So why do we need partial values or terms and not just partial substitutions? And a simple example is that because now pruning can operate on like fields of a product type, so kind of like parts of a compound type. So pruning can actually now remove part of a compound type. So the only way that I can represent this pruning operation is by having a partial term which represents a partial mapping from one type to another type, and then the other type can be pruned in some ways. So for example, what if I have a product type like AB C. And what if I want to prune the, okay, so prune the first projection. Then I get this type. So this is the original type, and this is the prune type. And if I want to represent some mapping which goes between these two types, so actually in pruning I always have to, so in the usual kind of pruning, what happens is that I have some gamma context, and then I have a gamma prime which is a pruned context. So gamma prime is gamma, but some entries are deleted from it. And then I have to construct two substitutions, so there should be one total substitution, so there should be a total f which goes from gamma to gamma prime, but there should be also a partial f minus 1 which goes from gamma prime to gamma. Because when I'm doing this pruning, I have to check that the prune thing is still well formed. And I can only do that by always maintaining this partial pruning substitution and then substituting every type in the context kind of in a recursive way, just going to the context and always using this partial f minus 1 to check that all the types are still sensible in the new pruned context. So that's why I need this partial f minus 1, and I need this total f in order to construct the solution of the original meta. So here I'm solving this alpha with this thing, and in the usual pruning I need the total forward substitution to construct the solution. Okay, so this is the case in usual pruning, but in this kind of pruning I have to use partial terms. So I have to have a term, so that there should be a term which is in this context. Maybe let's call this x. So there should be a t which has the prune type, and also the other way around. So if I have an x of type bc, then there should be a t minus 1 which has this type. And how can I define this? So t can be defined without any issue, because I can just say that that t is just a second projection of x, right? But what is t minus 1 here? So now I only have a bc, but I want to have a term with this type. So the only thing which I can do is to say that this is a pair of undefined and x, and this is a partial term. And if I have partial terms, so with partial terms, I could do that. I say that partial substitutions, so a partial subst is just a total substitution, but such that it contains partial terms. So now a total substitution can be a mapping from x to something and from y to something, but the something can be itself undefined. And this would be this is a more general notion of partial substitution, because now I can do a partial substitution such that it is only undefined for some like subfields of some product type or some sub-arguments of some function and whatever. So it is really more general than the simple notion of partial substitution, but it seems to be like more complicated, and I'm not sure that I want to implement this because some things just become much less efficient if you also have these partial terms or partial values. Like for example, if I have a partial substitution which maps variables to partial terms, and how can I compute the action of this kind of substitution? Compute the action of such partial subst. So then the representation of this partial substitution can be maybe, it can be just some map from bars to partial values. So this f can be just represented like this. But then the problem is that I want to define this operation. So like subst, which goes from like a partial subst gamma delta, and then I have a value in delta, and then I want to return a value in gamma. So this would be like the generalized version of the action of the partial substitution, which I'm already using in this implementation to do the pattern unification substitution on the right hand side. So I still need to define this function, but then the problem is, like, what happens if I want to do a subst f of some x sp? Then x is just a bound var, and sp is just a spine, and I know that if I apply f to x, so or if I do x substituted with f, then so this is a bound var in delta, and this is a spine in delta, and x of f is a value, is a partial value in gamma. But the goal is to have a partial value in gamma, which is like the result of applying this x of f to sp. Okay, so sorry, this does not return a value. This should return a term. Like this is like the generalization of usual partial remaining for items, right? So now this is a Tm in gamma, and the goal is to have, or this is a partial term in gamma, and the goal is to have a PTM in gamma, but the PTM should correspond to the substitution of xsp and not just the substitution of x. So I can also do a substitution of sp, and then I get something like a spine of terms in gamma. But now what I really have is just this xf and this spf. So I have a partial term, and I have a spine of partial terms, because the substitution already performs quoting into terms. But now if I want to get a term out of this, then what I could do is just to say that just do some kind of spine application of xf and spf, and it would work because it would be a partial term in gamma, and this is fine. But the problem is that in the spooning algorithm, and in other contexts as well, if I'm just plugging these two things together, then I do not perform any propagation of undefined. So this could be wrong, but the problem is just undefined is not propagated. And instead, what I would like to have is that I have this spine application and then I have to evaluate the spine application and then record this spine application. So I have to normalize the thing like all over in order to propagate undefined. And like what is an example for doing a propagation of an undefined thing? So if I have like an undefined entity and I take the first projection, in order to make the pruning algorithm work, I have to tell whether a term is undefined or not undefined. And it's much more efficient if I don't have to go into the term to see whether it's undefined or not undefined. But it would be a bit more convenient to have this immediately compute to undefined. But I'm not sure, because maybe it's okay if I just say that I am putting undefined in arbitrary places inside terms, and then whenever I have to check that the term is actually completely defined, I just have to fully traverse the term and just check everything. Maybe that also works, and that's a fine solution.
So I don't know if this helps, but so I think we can view a partial substitution as a composition of a total substitution. So first we have some weakening of gamma and then some total substitution.
That's already what we are doing. So the usual partial substitution is represented exactly that way formally.
Yeah.
So, and that kind of definition is not able to handle this situation.
Okay.
Yeah. Okay. So, I mean, this could work, but I have to look at it, and maybe it works fine. But this is just the place where I stopped because I recognize that here I have to do an extension which I haven't looked at before in any kind of way, and yeah. Okay, so this was the story about the unification algorithm from last week, and so the pattern unification I think works in a very nice way. And the pruning does not yet work in a very nice way, but maybe if I also figure out the pruning in a nice way, then I'm not sure. Maybe then I will write a paper about this algorithm. But now we do not have a lot of time for setoid type theory. I'm not sure. Should we talk about setoid type theory, or should we just call this a day for now? So we have 20 minutes from the official time. So should I talk a bit about setoid type theory?
Would you talk about the status of the implementation, or?
The status of the implementation is the same as about 1 month ago. It haven't changed. So yeah. So instead, I was working on like this elaboration and this unification algorithm, and I think it's not a waste even for the setoid type theory implementation, because I wanted to figure out the right way to do this anyway before I put it into setoid type theory. But the setoid type theory implementation is the same as 1 month ago. It's still not functional. Only the prototype implementation is functional now. So maybe Gergő, can you? So if we don't have that much time, Gergő, maybe you can be a bit more specific. Like, what do you want to see in the usage of setoid type theory? Let's go to setoid. Yeah, it is.
Oh, wait, I just realized. Have I been muted? Are you
No.
guys? Okay, so you could hear me before.
I mean, now I can hear you, but I'm not sure if you said anything before now.
Oh, okay. So I said that maybe like we could try and do ints as a pair of nets, such that we can define addition over it. Because that's the part that I'm curious about. Like, what does it look like when we try to do addition, and how does it look like that where it forces addition to be defined in a meaningful way, i.e., representation invariantly.
I'm not sure I understood this question. So
Okay, so we have do we have natural numbers?
Yes, okay. Just wait a moment because I have to quit from this Emacs in order to be able to go into the setoid type theory. Because of some stupid reason. What the heck? Okay, it seems that right now my setoid TT proto drove some stack error because I'm not sure why, because I changed some GHCs somewhere, and probably I do not want to figure it out, but I'm pretty sure that I can write setoid type theory just in a text file and I can answer all the questions, or I can write a setoid type theory in the style of the syntax of my implementation. So let me share the screen again. Yeah, so it seems that there was some bit rotting in the repository of the setoid type TT protocol, but I will figure it out. Okay, so what's the question?
Okay, so I just like to see a type which which really is a setoid, so which has some equalities. I was thinking maybe like, do we have natural numbers?
Natural numbers are not interesting. So
no, because then I was going to say, if we have natural numbers, could we have a pair of natural numbers to represent an int? That should be a setoid, right?
Everything is a setoid in setoid type theory.
Right, but
and
I mean,
So you want a quotient.
You want a quotient, right?
Yes.
Yeah, I mean we can have any kind of quotient. So
I think Gergő is interested, and me also, is how exactly like defining functions on quotient.
Exactly.
It works with the elimination principle. So maybe let's define some very simple quotient. Like let's define int set, And then let's define like what should be. There is a con, which is a not int, and then we have a quotient constructor, and which is, how does it look like? So if I have an A, B, C, D, then like okay, maybe there's a simpler way of doing it. It's like an A, B, and I think the simplest definition is that just the con of suc A, suc B is the same as the con of A, B, right? Is this correct?
Yes, I think so.
Yeah, maybe this is not the most convenient, but I think this is the simplest quotient for this definition, which is okay. Yeah, and then the question is, so how can we use it? And we have to use the eliminator. So that's it. So the eliminator has has an induction motive which goes from int to set, and then it has a witness for con, which is like for all xy or for all ab. I have an int d of con ab, and then I have a quote d which says that for all ab so how does this work? So on the left hand side I want to have the con d of this, so the con d of suc A and suc B should be the same as the con d of A and B, and moreover this should be transported over quote. So I transport in the quote or something like this. So these are like the induction motives and the induction methods, and from this
Quote or quote AB?
Sorry?
It should be transported over quote AB, right?
Yeah, I mean depends on if this is an implicit argument or not, or maybe yeah. Now this is an explicit argument if you are using the Agda syntax. Okay, so these are the induction motives and the induction methods, and then what we get is that we have a function which goes from any integer to the int b of I. So we get like this function which I usually we call e such that but then this such that actually has definitional equalities, such that if we apply int e to con d, then int e to con, then it reduces to con d. So plus we have the beta rule. Then I do not have to mention this int e here, but instead say that int e is just this whole function, and then the beta rule says that the int d applied to this, and then con ab is definitionally equal to con d of ab. Right, so we have this, and then we do not need to have any computation, any beta rule for quote, because this is proof irrelevant, so it returns in prop. And because prop is proof irrelevant, we do not need to have any beta rule for equalities. That's a difference between this quotient type and the cubical Agda definition.
Right, I have one more question. So which of these is things that you type into the Seto ETT type checker, and which of this is thing you get out of it?
So this is, so if I have an implementation, then this is like, or maybe I say that inductive, and maybe this is the syntax for declaring an inductive type. So this would be like an inductive declaration, and and this is what I get. So this is generated automatically for every inductive declaration.
Right, but and so the way it would work is that you actually get a name. Like, does int e has a name? Like, how do you use it? How do you refer to it? What does it look like when I then try to?
I mean, it's a design
it?
decision, but it could be just called int e or int elim. I mean, if in Coq you want to use the eliminator, which is generated for inductive definition, then it's the same. So it's just the original name, and then you just paste some elim or rec or whatever at the end of the name. That's how it works in Coq, and I think it's fine if you use the same thing. Maybe if you want to be a bit more sophisticated, then we can say. So if we want this system to be more generic, then there could be an alternative approach when the inductive declaration is first class in a way. So I instead of just these ad hoc declarations, I have a syntax. I have an internal syntax of inductive signatures, and then I can do some generic manipulations in inductive signatures, and then I have some operation, some operator, like a generic elimination operator, and the generic elimination operator is something which expects a signature as an argument. So then I would have like an elim of int sig, and the elim of int sig would give me the same elimination principle.
This is quite simple because if I understand it correctly, basically you define a function on a pair of naturals and you prove that it respects the quotient, and these are the inputs of the eliminator, yeah?
Yes.
And so this is basically exactly the same as you would do on paper if you would do it as a first year mathematician student in the university. But
yeah.
But in more generally, in Agda, you don't have the eliminators, but you have pattern matching. So this is maybe a too simple example, but what happens in general? Can you have an alternative, like pattern match type approach, or so somehow it feels to me that this does not show the full complexity.
I do not plan to do a pattern matching like thing for general quotient types. So I think that this can be already really complex to implement. So I do not have any plans to doing a pattern matching elaboration.
Yeah, but maybe not the implementation, but how would it look like, or what's the difference between potential alternative approach?
I mean, it's not really an alternative approach. It's just a syntactic sugar for elimination. So,
but is it really just syntax? Because if all you give to the user is this eliminator, then checking that a function is well defined is a simple matter of type checking, right? But if you allow pattern matching definitions, then there's some non-trivial action needed between the clauses of the definition and the quotient. Right? So I think it's not just a syntactic difference. It's not just like a flag you can turn on or off in in your pretty printer or your parser to get one or the other.
I mean, it's very complicated to elaborate a pattern matching definition to eliminators, but it doesn't give me anything more. So it should be exactly the same type theory.
Yeah, like you can define more functions using pattern matching than you can with eliminators. Is that what you're saying?
Right. Okay.
I'm asking, I'm not saying.
Yeah. That's correct. Okay, but if you look at this definition, then in cubical Agda we can define this definition, and we can also just give it like this, and now we have the same type in cubical Agda, right? So
yep.
So the question is what's the difference between using cubical Agda to define this quotient and using setoid type theory to define this quotient? And
you would hope that you have to do less housekeeping, for example, because you know that what you induct into is also a set, because it can't be anything else. That should make things simpler.
Yeah, so in setoid type theory I do not have to prove that the target is a set because everything is a set. So that's one thing which is easier. Moreover, I do not have to prove anything about quote because quote is proof irrelevant by definition. So if in Agda you want to define any function from this...
Oh, right, because in Agda you would need a fourth hypothesis or a third hypothesis to the eliminator, which would be that the trunk constructor is also kept correctly. Is that what you mean?
No. No, what do I mean? So, Okay, I'm not sure what I mean, but I think in Agda it can happen that we have to prove some, like for example, like if I want to return, for example, if I want to prove some equality about integers, right? So I want to prove an equality about integers, then the int d will return something in like an equality type, and then I have to prove a higher equality in code d, right? So, but in setoid type theory you never have to prove a higher equality. You only have to prove a first order equality, because every higher equality is irrelevant. So
but to be fair, those proofs are going to be very simple, because if you have isset then you can use that to prove the equality of the equality.
I mean, those proofs are...
You have to write it out, but at least it's going to be simple.
So those proofs are simple to a point, because so you have to mention isset to prove it, but then you want to do another construction which depends on the previous one. Then the previous one includes isset, and now you have to prove something about isset, that isset is also like a propositional thing, and it's a lot easier if it's just definitionally shortcut at the very first point when a higher equality comes up. So if I can just prove this by referral, then I can prove anything else which can depend on it also by referral. So I never get a size increase. Yeah, so that's one thing, and the other thing is that the transport computes more in setoid type theory than in cubical type theory. So in setoid type theory, for example, we have that the koi f, like a koi p x equals x, which is like this. regularity. So we have this in setoid type theory, but not in cubical type theory. And we also have that CoiQ is definitionally equal to CoiQP. Okay, maybe I can just, so like we have this split vibration things, and then we also get the stricter computation on inductive constructors. So for example, we get that okay, with this example we do not actually get any interesting thing. But for example, for lists we have that if I have a P which says that list of A equals list of B, and then I want to coerce like a nil of P, then that's definitionally equal to the nil of A. Okay, and then this is not in cubical lockdown. Or is it? No, I don't think. In general, it's not in cubical lockdown. It's definitely not in cubical lockdown if we have index type. Okay, maybe this is in cubical lockdown because list is not an index type, it's only a parameterized type. But if instead of lists I have vectors, so I have maybe a P is vec of A0 equals vec of B0, and then I can still have a nil of B, and this is also definitionally equal to nil of A. And then I'm pretty sure that this is not in Agda because vec is an index inductive type. So we have the stricter coercion computation, and okay, we also have like proof irrelevant equality, split vibration, stricter coercion computation, and we also have injectivity of inductive constructors and type formers by definition. So we have that, for example, a successor A, successor B is by definition, so the type itself equals the AB. And we also have that the suc A0 is by definition just bottom. And also for type formers, so for type formers we have that list of A, list of P is by definition. Yeah, and I think this is all of it, but if you add it all together, then I think it becomes very significant. So if you want to do lots of constructions with dependent types, then eventually we are going to get like lots and lots of transports, and it should definitely help if we have lots of proof irrelevance and we have more coercion computation. Like for example, a good example for like a good example in setoid type theory is that we want to prove that vector concatenation is associative. So vec concat is associative, and if we do this proof in setoid type theory, then we can just do, so it's exactly as simple as the proof for list concatenation associativity, because all the transport compute and we do not have to use any heterogeneous equality or any coercion computation or whatever. But maybe this also works in cubical lambda, but I haven't yet tried. So the generic elimination operator, it would compute. So the generic elimination operator would compute based on the signature.
Yeah, that would be at, let's say, compile time, or not? I mean, the signature, is that like a first class object?
Yeah, it's a signature. If the signature is first class, then the generic elimination computes on a signature. And if the signature is like fully first class, then this computation cannot really be performed fully at compile time, because it is also possible to have a neutral signature, right? So you can have a signature which contains a bound variable, and then you can do a generic elimination which computes up to the point that the signature is known, but the signature can be neutral. And then it gets stuck, but if you apply another substitution to it, then the elimination can compute even further, because now the signature is more known.
Right, yeah.
But that's pretty
that
speculative.
might not be so useful. Yeah, I mean, you cannot use a neutral eliminator if the signature is neutral. Then you cannot use it in any way, can you?
I mean, if a signature is neutral, then you know that we know that we have elimination for any signature, even for the neutral ones. But if I have a neutral signature, then basically the type of the elimination principle is also neutral. And like the arguments which I have to supply to the elimination principle also have these unknown types. But I'm not sure. I mean, I can imagine that maybe in some setting, like in some very generic programming,
right, yeah.
It's possible that we just want to like do some higher order, like we want to combine multiple signatures together using some operation which is user defined. And because of these operations, we have some neutral parts in signatures, but we still want to compute with them and use elimination.
Yeah, okay. Yeah, I see.
But this is very speculative. I have never seen anything like this implemented in a usable way.
Well, the gentle art of levitation is something like that.
Yeah, but I haven't seen the art of levitation implemented in a usable way, really.
No, I haven't seen it. No.
I mean, in setoid type theory, it's very likely that I won't try to do this. I will try to just do this Coq style. You just give a signature and then you get an eliminator. But in many cases, it's very convenient if you can go beyond this. So I want to get not just an eliminator from a signature, but I want to get much more from a signature.
Yeah, I was thinking that because if you use just this inductive type definition, and you also have to perform the checks that it's the positivity checks are have to be done, right? So it's consistent. But if you have something like gentle art of levitation, then the construction of the signature itself makes sure that it's consistent.
Yeah, but
so that's like a bonus there.
I mean, it's a bonus, but actually not really, because the same, like the positivity checking is just baked into the type of the signature constructors. So at the end, we still have to perform type checking on signatures to see that they are well typed, but the positivity is baked into the types in the signature. And I think that's
yeah. But I mean, you already want to create a type checker, so then you don't have to create a separate algorithm for the positivity checks. I mean, in that sense,
yeah,
it's a bonus.
Yeah, that's a bonus. But I would want to try to do this positivity checker by trying to not create a separate positivity checker, but instead saying that that maybe, how can I? So I just want to have like a language of signatures, and then the signature should be some kind of telescope. And okay.
Yeah, if you could first translate this style of signature to the like gentle art of levitation style or something else, then if that translation is simple enough, then it will be quite nice, I think.
Okay, I'm not sure. I think I would have to implement something which looks like a separate positivity checking, but but what I've been thinking a bit about is that so I want to say that the type theory of signatures looks a bit like a level from a two-level type theory, or because then, like in signature, I can refer, like inside the signature, I can refer to things which come from the type theory. And it looks a bit like a two-level like separation of different type theories. And what I'm thinking about is like if we can do it in a way which is similar to a two-level type theory, but haven't yet worked out.
Yeah, that might be a subject for another meeting.
Okay, so do we have anything else for today? Maybe we can do a bit of planning, like what should do next week, because now I'm kind of running out of like code which can be presented. So I don't have any new Setoe type theory or elaboration zoo or whatever, and I'm not confident that I can generate new code in fast enough. So but I can still talk about just some stuff which don't have implementation, or other people can also talk about other kind of topics. So is there here someone who wants to talk about things related to type theory implementation? The answer is no.
Maybe just throw it in the chat, and maybe during the week somebody will.
Yeah, okay. I will throw it in the chat, but I think it can also work if we just maybe like the people who show up here just show up, and then we can decide like if there is anything interesting that we can discuss. I mean, there are lots of other seminars which also work this way, that people just show up and then people decide what to do.
Yeah, true.
Okay. Okay, then see you next time.
Just a quick note before you leave, András. Yesterday, while we were at the end of the seminar, we were also mentioning Idris at the type theory seminar, and I've been looking up some Idris stuff lately, and I've noticed that everybody talks a lot about your small TT implementation in his talks and on his blog and such. And I noticed that in your small TT repository, you have a note that as of November 2020, this implementation is obsolete. And I wonder if you have notified him about this or not yet, because I think he would be interested in the development of this stuff.
Yeah, I mentioned this a while ago, but actually the Idris implementation does not use. So it's
inspired by.
It just takes it takes like some hints from the actual small TT implementation. It does not use the actual small TT evaluation. So
Yes. But if you have a better version of it, then he might be able to take better hints. I don't know.
Yeah, I mentioned. So the old implementation in small TT is a bit overcomplicated, and in Idris it's something which is simpler, but it's also slower. And the new version of glued evaluation is a lot simpler than the small TT, and it's roughly has the same performance. And I mentioned this several months ago to Edwin, that now there is a simpler version, and maybe it's worth to try to implement it in Idris as well.
Nice. I guessed that you have already done so, but I just wanted to make sure that the information is passed on.
Yeah.
All right. Thank you very much.
And the simpler version comes from OLEF. So OLEF should be thanked for the simpler version. Maybe.
Then thanks Olaf. I hope to see Idris 2 being very awesome. And also this satellite TT being very awesome to use. I'm kind of fed up with the speed of Agda. Waiting 40 seconds for type checking the file is not the most pleasant experience. All right. Goodbye.
Okay.